so called AVL because this AVL tree was invented by GM Alonso Belsky and EM Landis. So I may write here this tree was invented by GM Adelson Adelson Belsky and EM Landis. So that's why the tree is named AVL in honor of its investors. The tree is named AVL in honor of its inventors. So that's why. So here Adelson Belsky. So you can say that AV and here is Landis. L is here. That's why the name is called AVL tree. So it is a height balance tree. I can say that it is a height balance tree. All right. It follows the property of binary search tree. The elements are arranged in terms of binary search tree approach. That means the left value is less than your parent node value and the right child value may be greater or equals to your parent value. Now, what is the height balance tree? So, a tree is said to be height balanced if each node's balance factor lies between -1 to +1 through 0. That means if the balance factor is lying -1 or 0 or the balance factor node is +1, then we can say that the tree is balanced. If every node of that tree is carrying the balance factor value within this range, that is -1 to +1 through 0, then we can say that the tree is the height balance tree or a AVL tree. So we can say that the balance factor is determined by the formula balance factor is how much height of left subtree minus height of right subtree. So find the height of the left subtree, find the height of the right subtree. So that value will give you the balance factor. If the balance factor is lying between -1 to +1 through 0, then you can say that the tree is maintaining the AVL tree property. Suppose this is tree with let's say 4 number of nodes. So how to find the balance factor of your node 1, node 2, let's say node 3, this is the node 4. So the node and balance factor is the height of the left subtree. So left subtree is 2 and the right subtree is 1. So the balance factor is 2 minus 1, it becomes 1. And the balance factor 2 is the left subtree height is 1, there is no right subtree, so that's why 1 minus 0. So left subtree is 1, the right subtree is 0, 1 minus 0 is 1. And this is a leaf node, 4 is a leaf node, and 3 is also leaf node. So there is no left subtree, there is no right subtree. So that's why 0 minus 0 is 0. And similarly, 3 is a leaf node, its balance factor is 0. Now, this tree is called your AVL tree because each node is having the balance factor between -1 to +1 through 0. If I am going to draw another tree, let's say this is tree 1. Let me draw one more tree. So I can say that this is a AVL tree. Similarly, if I am going to draw one more tree, suppose this tree is containing, let's say that, few nodes. Right. So what is the height of the leaf nodes? So 0, because there is no left subtree, there is no right subtree. It is also 0, it is also 0, it is also 0. Sorry, this is also. Now, all the leaf nodes are having the balance factor 0. Then think about the balance factor of this node. Alright, if I am going to name the node as 1, 2, 3, 4, 5, 6 nodes. So the balance factor up to second node is how much? Left subtree is having the height 1. Right subtree is having height 1 also, 1 minus 1, it becomes 0. Similarly, the balance factor of your node number 3 is how much? Left subtree is 1 and there is no right subtree, so 1 minus 0, that is 1. Then what is the balance factor of your node number 1? That is left subtree height 1, 2. So height is 2, right subtree is having the height also 2 nodes 2. So 2 minus 2, it is 0. So every node is having the balance factor within that range, that is -1 to +1 through 0. So that's why it is also a AVL tree. If I draw one more tree, just think about the tree which looks this way. Okay. Is it a AVL tree? Suppose this is my node number 1, this is node number 2, this is node number 3, this is node number 4, this is the node number 5. Now, the height of your, now the balance factor is of node number 1, the height of the left subtree 1, 2, 3, and the right subtree is 1, 3 minus 1, that is 2. So, here the balance factor is not lying between -1 to +1. Alright, it's not lying through 0. I can write that -1, +1, 0. So here it is not lying within that range. So that's why it is not a AVL tree. It is not a AVL tree. So if I say that what is the balance factor of your node number 2? So left subtree, that is 2. Right subtree, there is no right subtree, so 0, so that is 2. 2 minus 0 is 2. So what is the balance factor of node number 4? There is no left subtree, 0. There is one node in the right subtree, so 1. So 0 minus 1, that is your -1. And this is a leaf node, balance factor is 0. This is a leaf node, the balance factor is 0. Now the node number 1 and node number 2, which are having the balance factor which is beyond the your AVL tree balance factor range. So 2 is not lying within minus 1, 2 plus 1 through 0, and the non-negative balance factor 2 which is not lying in this range. So that's why this is not a AVL tree. If a tree is not going to satisfy the property of the AVL tree, then we need to rebalance it. So how you are going to rebalance it? Let me discuss. So next is a non-AVL tree. A non-AVL tree can be converted to AVL tree by using the rotations. So we have 4 types of rotations available. 4 types of rotations. The first one is called LL rotation. LL rotation. Second type is called RR rotation. Third type is called LR rotation. And fourth type is called RL rotation. Let's move on to discussion of each type of rotation. It's called LL rotation. So what is the meaning of LL rotation? The new node is inserted. The new node is inserted in the left subtree of the left subtree of critical node. That means, suppose I am having 3 nodes. Now just think about, this is the first node and the second node inserted at the left side of your first node, and the new node at 3 that is also inserted in the left side, in the left subtree. Now find the balance factor. So the balance factor of node number 3 is 0 because there is no left subtree, there is no right subtree. What is the balance factor of node number 2? The left subtree height is 1, right side there is no right subtree, so that's 0. So 1 minus 0, that is 1. And what is the balance factor of node number 1? The height of the left subtree, that is 2, and the height of the right subtree is 0 because there is no right subtree. So 2 minus 0 becomes 2. So that's why the node number 1 is called the critical node. So the new node, that is 3, is inserted in the left subtree. Yes, left subtree of what? The critical node. So now it is not a AVL tree. If you want to convert this non-AVL tree to AVL tree, we need the LL rotation. So what the LL rotation is that we have to rotate the tree in clockwise direction at the critical point. So if you are going to rotate the critical point, so how the tree is going to look like? So 2 will move to your position of your first node. So that's why 2 comes to here. I cancel that after rotation. How it is going to look like? 2 comes to here. 1 goes to the right of node number 2, and this is your node number 3. So just imagine that. So this is the node number, this is not the value. So what is going to happen here? I can say that, so your height of the tree is now your 3 and 1 nodes are leaf nodes. So that's why the balance factor is 0, this balance factor is 0, and the balance factor node number 2 is what? The left subtree height minus right subtree height. So left subtree height is 1, right subtree height is 1, 1 minus 1 becomes 0. Now each node is satisfying the range value, that is minus 1 to plus 1 through 0. So that's why it is a AVL tree. So we converted a non-AVL tree to AVL tree by doing your rotation. That is called the LL rotation. Alright, is it okay? Then next type of rotation is called your RR rotation. What is the meaning of RR rotation? The new node is inserted. The new node is inserted in the right subtree of critical node. Right subtree of critical node. For example, a tree which looks like this way. Now, this is the node number 1, this is the node number 2, this is the node number 3. So, new node that is N3 is inserted at the right subtree of your right step to the critical node. This N1 is a critical node because the valence factor is lying out of the range. What is the valence factor of N3? 0. What is the balance factor N2? Left subtree is 0, right subtree 1. So that's 0 minus 1, it is minus 1. And what is the balance factor of N1? There is no left subtree, that's why 0. Right subtree height is 2. So I can write that 0 minus 2, that is minus 2. So as the balance factor of N1 is lying out of the range, so that's why N1 is called the critical node. So the new node N3 is inserted at the left subtree of the critical node, so that's why it is called the new node is inserted at the right subtree of the critical node, so that's why it is called RR rotation is needed. In the RR rotation, we are going to rotate the nodes in the anticlockwise direction at the critical node. So now the tree is going to appear as, you see it, that N1 will move to towards the left side of N2, N2 will move to N1, so N2 comes here, then N1 goes to the left child part of your N1, N1 goes to the left child of N2, and N2's right child will be N3. Now measure the balance factor. So N1 is a leaf node now, balance factor 0. N3 is a leaf node, balance factor 0. N2 left subtree height is 1 and N2's right subtree height is 1. So 1 minus 1 becomes 0. So that's why after doing the rotation, a non-AVL tree, this is a non-AVL tree. The reason is that your N1's balance factor is minus 2. Now we did the RR rotation. After doing the RR rotation, your tree becomes a AVL tree because every node's balance factor is lying within the range, that is minus 1, 0 and plus 1 range. So that's why we converted a non-AVL tree by doing the rotation, that is called the RR rotation. LR rotation. So what is the meaning of LR rotation? The new node is inserted in the right subtree of the of the left subtree of the critical node. What is the critical node? The critical node which balance factor is beyond the range, that is -1 to +1 through 0. If the critical node is said to be critical node if its balance factor is not lying the range, that is -1 to +1 through 0. Alright, the new node is inside the right subtree of the left subtree of the critical node. Now let me draw. This is a node number 1. I inserted node 2, and here is node 3. Now just imagine that your new node is inserted on the right subtree of the left subtree of the critical node. So N1 is critical node because what is the balance factor of N3? 0. What is the balance factor of N2? -1, 0, and the height of the right subtree is +1. So 0 minus 1 is -1. And what is the balance factor of your N1? Your left subtree height is 2, the right subtree is nothing, 0, 2 minus 0, that is 2. So that's why we can say that this is a non-AVL tree. It is not a AVL tree. If it was not a AVL tree, and this non-AVL tree can be converted to your AVL tree by doing the rotation. What the rotation will do? The first you apply your anticlockwise rotation at node number N2. If you are going to do that one, then what will happen? This is your node number 1. Then if you are going to do the rotation, N3 will go to the position of N2. So N3 comes to here, and N2 will go to the left child of your N3. Now after doing your anticlockwise rotation, a tree looks like this way. So now measure your balance factor. So balance factor N2 is 0, balance factor N3 is now +1, left subtree is 1, right subtree is 0, 1 minus is 1, and the balance factor N1 is left subtree height is 2, 2 minus right subtree is 0, 2 minus 0, that is 2. So still there is not a AVL tree after doing the anticlockwise rotation, but it is your LL rotation. Now the tree, your new node N2 is the left subtree, instead of the left subtree of the critical node. So now it behaves as if the LL rotation. I can show you that the same type of issue found here in the LL rotation. In LL rotation, we are going to apply your clockwise rotation at the critical node. Now you can see that one. The same type of process we have to apply. So here we are going to apply the rotation at the node number N1. If you are going for one more rotation, now we can say that N3 comes to here, N1 goes to the right subtree, and N2 becomes the left child of your N3. Now just imagine the balance factor. So balance factor N2 is 0, balance factor N1 is 0, balance factor N3 is left subtree height is 1, right subtree height is 1, 1 minus 1 is 0. Now it becomes a AVL tree. So in your LR rotation, you are doing your two types of rotation. Double rotation you are applying. One is towards your anticlockwise, another is your clockwise, to make a non-AVL tree to AVL tree. So be careful, we are applying just below to the critical node, the first rotation, another is at your critical node to convert your non-AVL tree to AVL tree in case of LR rotation. Let's go for your next AVL rotation, that is called RL rotation. What is RL rotation? The new node is inserted. I can write the new node is inserted inserted in the right subtree, in the left subtree, just reverse of your AVL rotation, in the left subtree of the right subtree of the critical node. For example, just think about a case here. I am having the first node N1 is here, and here is your N2, and N2's left part is your N3. The new node is N3 is inserted in the left subtree, yes, in the left part, and left part of the right subtree of the critical node. So N1 is critical node because the balance factor value is not lying in the height balance tree range. So what is the balance factor N3? 0. Balance factor N2, left subtree height is 1, right subtree height is 0. So 1 minus 0 is 1. Then what is the balance factor N1? Left subtree is 0, right subtree is 2. So that is minus 2. So everyone is satisfying the balance factor range except the node number 1. So that's why it is a N1 is a critical node. So what should we do? First we have to convert your given AVL non-AVL tree. This is non-AVL one. So we have to apply first rotation at N2. We are going to apply the first rotation at N2. So what will happen? Your N3 goes to the position of N2. So N3 comes to here, and N2 becomes the right child of N3. Now this tree is still a non-AVL tree because the balance factor of N2 is 0, balance factor of N3 is minus 1, balance factor of N1 is minus 2. So after doing the first rotation in the clockwise direction, so in case of your AVL rotation, we are doing the first rotation anti-clockwise. In case of your AVL rotation, we are doing the first rotation in clockwise. Then you apply your second rotation at the critical node towards your anti-clockwise. So what will happen? N3 will comes to here, N1 goes to here, and N2 moves to the place of your N3. Now it is a height balance tree or AVL tree because the height of N1 is 0, height of N2 is 0, height of N3 is left subtree height is 1, right subtree height is also 1. So 1 minus 1 becomes 0. So now it is a AVL tree. So we converted a non-AVL tree to AVL tree by doing your two types of rotations. So in your AVL rotation, we are doing the two types of rotations to make a non-AVL tree to a AVL tree. So construct, question is given to you, construct a AVL tree construct an AVL tree from the given values. What are the given? 10, 70, 35, 45, 90, let's say 15, and so on. So 6 node values are given. So first value is 10. So we'll arrange in terms of your binary search tree. So we place the first value is 10. Then next value is how much? 70. 70 is greater than your 10. So we placed on the right child. Then next value. So what is the balance factor? Balance factor is here is 0, here is left subtree is 0, right subtree is 1, 0 minus 1. So it's your AVL tree, no issue. We can insert next value 35. 35 is greater than your 10. We go to right side value 70. So 70 and 35, so 35 is less, so we placed here. Now find measure the balance factor. If you're going to measure the balance factor, this one is 0, this one is plus 1, where left subtractor is 1, right subtractor is 0, 1 minus 0 is 1, and the balance factor of your 10 is how much? Left subtractor is 0, right subtractor is 2, so 0 minus 2 minus 2. Now, what should we do? If you recall, we can say that it belongs to your what type of rotation? It belongs to your RL rotation. Just look at here. N1 right child is N2, N2's left child is N3, and same thing happens here. 10 right child is 70 and here is 35. So what should you do? We should apply the RL rotation. If you are going to apply the RL rotation, so here you are going to apply your RL rotation. It is a non-AVL tree, we have to apply the RL rotation. In RL rotation, first you have to apply your clockwise rotation at the 70. So you can say that here 10, then 35 goes to the place of 70, then 70 comes to here. And once the first rotation is over, we are going to apply the second rotation at the critical node. So if you are going to apply, then what will happen? 35 comes to here, then 10 comes to here, then 72 goes to the place of 35. Now the balance factor, if you measure, the balance factor will how much? 0. This one is 0, this one is also 0. So it is a AVL tree. Once this AVL tree is formed, then you can go for the next element insertion. What is the next element that will be inserted? That is 45. So now if you are going to insert the 45, where should you insert? 45 is greater than 35, you go to right side, and the right side value 70, so 45 and 70, so 45 is less than, so we should place here. That's here. We have to again measure the balance factor. The balance factor, this one is 0, 10's balance factor is 0, 70 balance factor is how much? Left subtractor is 1, right subtractor is 0, so it is no more 0, it becomes 1. And what is the balance factor of your node number 35, which contains 35? Left subtractor is 1, right subtractor is 2. So I can say that there is 1 minus 2, that is your minus 1. So still all the nodes are following the range of AVL tree values, minus 1 to plus 1 through 0. So that's why it is AVL tree. We can go for the insertion of your next elements 90. We are going to insert the next element 90. So 90 is greater than 35. You go out, you go to the right side 70, and the 90 is greater than 70, we place the 70 here. If you have placed the 70 here, again you have to measure the balance factor. So what is the balance factor of your 70? 0, 45 still 0, 10 still 0, 70 is how much? It will be left subtractor height is 1, right subtractor height is 1, 1 minus 1, it becomes your 0. The new balance factor 70 is 0. Now what is the balance factor of your node which contains 35? So left subtree of node which contains 35 is 1, right subtree is 2, so 1 minus 2, that is minus 1, still it is minus 1. So if you check every node's balance factor, it is lying within the range of AVL tree. So that's why we can go for the next element insertion 15. If you are going to insert the 15, what will happen? So 35 and the 15 less than 35, we will go to the left side value is how much? 10. So 15 and 10, so 15 is greater than 10, we have to place as the right of your 10. So what is the right of 10? We place, that is your 15. Once you place the value, then we will measure the balance factor. The balance factor 15 is 0, 45 is 0, 70 is 0, 7 sorry, this is not 70, 90. This is the 90. So we have inserted after 45, 90 is inserted, so it is a 90. So 90 value is 0, 70 is 0, and 35. So what is the balance factor of 10? Balance of 10 will how much? Left subtractor is 0, right subtractor is 1, 0 minus 1, so it is no more 0, it is minus 1. And the balance factor of your node which contains 35 is how much? Left subtractor has 2, right subtractor has 2, 2 minus 2, it becomes your 0 now. So if you look at every node, so 15 balance factor is 0, Your 45 balance factor is 0, 90 balance factor is 0, 70 balance factor is 0, here it is 0, here is also 0. So after inserting the 15, your tree is a AVL tree. So I can say that this is the final AVL tree after inserting the values given in the question. So let's go for one more. So next question is construct the AVL tree from month names. So we have January, we have February, we have March, April, May, June, July, August, September, October, November and December. So we have to construct a AVL tree. So the first is January, we inserted here. So January, balance factor 0. So no issue, we can insert the February. So F and Z. So I can say that I will insert the left side. So February J inserted here. Then is March. March is greater than your value of ASCII value is M and ASCII value of J. So we can say that M is larger, so we'll place here. March is placed here. Alright, and the balance factor will have much 0, 0, and January balance factor will be also 0. Next is your April, A. So April begins with A. So A is less than J, we go to the left side. A is less than F, will go to the left side. So April is written as left side of your February. Then find your balance factor. Balance factor April is 0. This is not going to be your 0. It will be how much? 1 minus 0, 1. This is 0. This is how much? 2 minus 1. So it becomes 1. So this is the current balance factor of each node. Still it is a AVL tree. So we can insert the next element, that is May. So M is greater than J, you go to this side. March. So March, here is M, A, then R is here is Y. So Y is greater than your R. We will place your May here as the right child. Now you measure the balance factor. So what the balance factor will be? So I can say that balance factor May is 0. Balance side April is 0. So this one will how much? Left subtree is 0, right is 1. So 0 minus 1, it becomes how much? Your minus 1. And what is the balance factor of your February? Still 1. What is the balance factor of January? So left subtree is 2, right subtree is 2. So 2 minus 2 becomes your 0. So we can say that all the nodes are lying within the AVL tree range. So we can go for the next element insertion, that is the June. So June, so here January, JA, so U is greater, so we go to the right side. March, so M and J, so J is less than your M, so we'll place as the left side. So June is placed here. So after placing the June value, then you have to measure the balance factor. Balance for June is 0. So May is 0. The March is no more your balance factor minus 1. So you can write that balance factor as your 0. The recent balance factor is 0. So left side is 1, right side is 1, 1 minus 1, 0. And April is 0, February is 1. I kept it. The January, left subtree is 2, right subtree is 2. So still it is 0. So this is the way we found that every node's balance factor is lying within the AVL tree range, so that we can go for the next element insertion, that is your July. So now J is greater than your JU, here is JA, January, So you go to the right side is March, show June and March, so March is greater than July, so that's why you go to this here. Your left side node is June, so Jun, and here L, so I can say that your L is less than your N, so I can place as the left side here. I'll write here July. Now you have to find the new balance factor. What the new balance factor? This is 0. This will be no more 0. This will be how much? Left side to 1 minus 0, that is 1. This is 0. And March balance factor will be how much? March node. Left side is 2, right side is 1. 2 minus 1, it is no more 0, it is 1. And April and February remain same. January, left subtree is 2, right subtree is 1, 2, 3, 2 minus 3, so it is your minus 1. Now look at 0, 1, 0, 1, 0, 1, minus 1. So still it is a AVL tree. I can go for the next element insertion, August. If you are going to place the August, where you should place? So here is A is less than J, we go to the left side. F is less than, so your F is greater than your A, so you go to the left side. So left side value is April and the value which August is here. Now what should do? So P and here U is greater than your P, so we will place as the right child. You will write here August. Is it okay? Now we have to measure the new balance factor. The balance factor for August is 0. April is how much? Left subtree is 0, right subtree is 1, so it is no more 0, it is your minus 1. And this height, so February I can say that left subtree is 2, right subtree is 0, 2 minus 0, that is a plus 2. Now it is going out of the AVL tree balance factor range, so we need the rotation. And other part remains same. January I can say that 1, 2, 3, left side is 3, 1, 2, 3, so 3 minus 3, it becomes 0. So every node is following your AVL tree balance factor range except your non-February node, which is having the balance factor 2. If it's so, then just look at what type of. So in this left subtree and the new node inserted and the right part. So what type of rotation you are going to apply? So just recall. So I can say that this belongs to your LR rotation. The new node is inserted in the right subtree. Yes, new node is inserted at the right subtree of left subtree of the critical node. February is critical node. So we have to apply the first rotation at April, then we'll apply the second rotation at February. So 2 rotations we should apply. Now what will happen here, I can say that the first rotation I'm going to perform. So January, this is your February, I'll apply your rotation at April. So August is here, then April is here. I'll apply the anti-clockwise as per your LR rotation. The first rotation will be done here in the anti-clockwise. So if you are going to that, August goes to the April position and April becomes the left child of August. The February is at Z. Then I am writing here March. The remaining nodes I kept as it is. Then this is your June. This is your May. This is your July. Now after doing the rotation at your April, I will apply the rotation at February. So again you have to apply the rotation at here, because in LR rotation we have to apply the 2 types of rotations. So what will happen here? So this is your January. Then what will happen? August goes to the place of February. This is August. Then this becomes your position of the February. Then this becomes position of April. Okay, so we arrange this way. August moves to the February. February becomes your right child of August, and the uppermost to the position of here. So we have written the then remaining nodes you have to arrange as it is. So this is your March, then this is right child of March is May, then this is your June. I'm writing rewriting the content from the right subtree of your January, then this is the July. Okay, now you just find your balance factor. The balance factor, I can say that this is your 0, this is all the lymph nodes are 0, 0, 0, and this is your June. Balance factor is left subtree is 1, right subtree is 0, 1 minus 0 is 1 plus 1. And what is the balance for March? Left subtree is 2, right subtree is 1, 2 minus 1, that is plus 1. So what is the balance for August? Left subtree is 1, right subtree is 1, 1 minus 1, 0. What is the balance factor of January? Left subtree height is 2 and the right subtree height is 3, 2 minus 3 is minus 1. So every node is following the balance factor value within minus 1 to plus 1 through 0. So that's why it is AVL tree. After doing your LR rotation, we converted a non-AVL tree to AVL tree. Then we can go for the next element insertion, that is your September. We are going to insert the September where we are going to insert it. So now September we can say that S greater than January, go to the right side, right till March. So September is greater than March, go to the right side, May and the September. So September is greater than May, so we will place here as the right child. This is the right child. Now the balance factor will be how much? September is 0, this is 0, this part will not be changed. So now January will how much? 1 minus 0, 1, this is how much? Your 0 minus 1, this is no more your 0, it will be minus 1. Okay, because it is the right child. Right, then what is the value of your March? 2 minus 2, it is your 0. Left subtree is 2, right subtree is 2, so 2 minus 2 is 0. Then what is the balance factor January? So height of the left subtree 1, 2, height of the right subtree 1, 2, 3. So 2 minus 3 is minus 1. There is no issue. So all the nodes are lying within the AVL tree range. So we can go for the next element insertion, that is your October. So after applying your rotation in clockwise direction of September, the tree looks like this way. So October moves to the place of September and September becomes the right child of your October. Now you measure the balance factor. So balance factor is written as it is. So the May is minus 2 because left subtree is 0, right subtree is how much? That is 2. So 0 minus 2 is minus 2. So we did one rotation here and the second rotation will be at the May. So that will be clockwise direction. So if we are going to apply the clockwise rotation, then the tree is going to appear this way. So just look at here, October moves to the position of May, yes, October moves to the position of the May and May becomes your left child of your October. Then October's right child is September as it is. Now you try to find the balance factor. Show the balance factor. If you look at, everyone is now in your within range. Now you just insert the next month after October is November. We are going to insert November, then measure your balance factor. So now balance factor, you will find that after inserting your November, the balance factor of your January is minus 2. Now this critical node is January and the new node is November. So January is having critical node value minus 2 and the new node is November, which is inserted in the right subtree. So that's why we have to apply the RR rotation. In the RR rotations, we are going to apply single rotation at your critical node, that is your January. You are going to apply the single rotation in anticlockwise direction at January, then the tree is going to appear this way. So March will move to the January position. March becomes your position of the root node. Then March left child is right child is October. Yes, October's left child is May. We have written that. October's right child is September. We have written that. Then May's right child is November. We have written that. Then if you are moving in your anticlockwise direction, January will be the left child of March. So January is the left child of March. Then January's left child is August. We have written that. August left and right is April and February. We have written that. Then your June is the right of your January. So that's why you have written that June is the right of January and June's left child is July. We have written that. Now you measure the balance factor. All the nodes are lying within the AVL tree balance factor range. So we can go for the next month insertion. So we have inserted November. We'll go for that December. So if you are going, okay. So if you insert the December, D is less than M. So J, so D is less than J. We move to August. So August is less than your December D. So that's why we move towards the right. Right child is your February. February is started with the letter F and the December D. So F is greater than D. So D will be inserted as the December, which starts with D, which will insert as the left child of February. Now you measure the balance factor of each node. So first we assign the balance factor of leaf node as 0, 0, 0, 0. Then what is the balance factor of your February? 1 minus 0, that is 1. So balance factor of August, left subtractor is 1, right sub 2, so that's a 1 minus 2 is minus 1. June, so June left subtractor is 1, there is no right subtractor, that's why 1. May, left subtractor is 0, right subtractor is 1, so 0 minus 1 is minus 1. October, then I can say that left subtractor is 2, right subtractor is 1, so that's why 2 minus 1 is 1. January, left subtractor is 1, 2, 3, right subtractor is 2, so 3 minus 2 is plus 1. And March is how many nodes? Your left subtree 1, 2, 3, 4, right subtree is 1, 2, 3. So I can say 4 minus 3, that is 1. After inserting December, your each node is following the balance factor range within minus 1 to plus 1 through 0. So that's why it is a AVL tree. Now we have inserted 12 months and we have constructed a AVL tree from the months of your English calendar. This is the final AVL tree after inserting the 12 months.